Hello. So we're going to learn about capacitors. So what you probably heard about capacitors is that they're used to store charge. And let's talk about how that works and maybe like why it's relevant as well. So basically, a capacitor is usually like two metal plates that are separated by some sort of insulator, like usually air. So between these two capacitors, these are like conductive, charges are like free to move around, and between them, nothing can really move. And we typically connect them to some sort of battery, and that's what we use to charge them up. So let's talk about how this works. You have basically a positive and a negative end of the battery, and this positive end is going to be repelling the charges on this wire. So remember, there's electrons and protons on this wire, on these plates, everywhere really, and so this positive charge is just gonna sort of repel these three. Let's do one actually. Let's do one proton. It's going to repel this one proton to move all the way across to this positive plate. Except it can't go any further because remember air is an insulator. So now this proton is going to repel the charges on this plate. So you have this like say positive charge and a negative charge, except this positive charge, let's see if I can select this, is going to be repelled and it's going to move all the way around. So that's going to happen again, where you're going to have like this positive charge basically be repelled by, by this positive charge right here, and it's going to start moving more. And this is going to do the same thing. Another positive charge from here is going to come off, and there you'll have like another net negative. So there's a lot of charges here, but I'm just kind of showing like the net negative or the net positive. So this one's going to move around. And so on until you have this buildup of all these positive charges here and all these negative charges on the other plate. And this is going to be the same amount as we kind of just saw in the symmetry. So when is this going to stop? Like you can't keep building up charges forever. There's obviously a finite amount of work that you can do. So what eventually will happen is that you have a certain amount of positive charge here, and a certain amount of positive charge here. So like the next positive charge, let's place it somewhere in the middle. It's going to be repelled by this guy, but it's also going to be repelled by this guy. And so when you reach that balance where they're repelling them at with the same force, then charge is no longer going to be moving. And that's when you kind of reach your steady state where this capacitor is now charged up. And I know I went through it pretty slowly, but this is a really fast process. And so this will happen almost instantaneously. So that's kind of the basics of how a capacitor will work. I said that I would talk about how they're used a little bit, and the main applications that you see from capacitors are one, just to store charge in general. Capacitors are also used very widely in sensing mechanisms. So, for example, your touchscreen is capacitive. How that basically works is when you place some sort of, let's see, finger, that's going to change the capacitance of the capacitor, and this is something that you can detect. So they're used that way. Yeah, they're used in a whole bunch of places. I'm not really the most educated about this, but yeah. So we got a basic overview of capacitors. Now let's do series and parallel. So we're going to start with parallel actually. So with resistances, we saw that like the series was the simpler one. With capacitors, it's actually the opposite. So let me draw another circuit. Oh, this is way too big. I'll put my battery on the side, and I'll just have a bunch of different capacitors. Let's say we have maybe 3 of them. So we do our thing, like these positive charges start moving, and eventually each of these build up with some positive charge. And then correspondingly, each of the negative plates build up with some negative charge. So this doesn't really necessarily have to be the same amount of charge on each capacitor, because remember, like, this is like a whole another circuit, basically. So we're really just analyzing 3 different circuits, because in parallel, the key observation is that the voltage across any capacitor is going to be the same as the voltage across the battery. And so we can just treat these as individual circuits. All we really need to know is the voltage across them. And yeah, that's the key observation here. So let's talk about like how we would do some sort of equivalent capacitor that mirrors the behavior of these 3. So maybe this can be my C equivalent. C stands for capacitance. And then this capacitor is somehow going to mirror the behavior. So the first thing we can ensure is that the voltage across this capacitor is going to be the same. And we already know that it is. And so the other thing that we can ensure is that the charge on this plate is going to be the same as the positive charge here. And the same thing we can say about the negative charge. So the main relationship we're going to leverage is that Q1, EQ, is equal to Q1 plus Q2 plus Q3. And Q stands for charge. So before I kind of expand this, let me talk to you about the fundamental equation for capacitors. It's kind of like how we have Ohm's law for resistors. For capacitors, we have the relationship Q is equal to CV, where C is capacitance and V is voltage. So what this basically means is that as the voltage goes up, you have the ability to store more charge. And as the capacitance goes up, you also have the ability to store more charge. So the capacitance one, it basically just means that because capacitance is defined as the ability to store charge, and we can talk about what the quantity is in general, but it's basically some sort of constant that is dependent on like the area of the plates, the distance between the plates, and some otherworldly constants. So we have this relationship, and we're going to use it. So we can say that Q EQ is equal to C1 V1 plus C2, and remember the voltages are the same, V, plus C3 V. And this guy can be just written as C equivalent times V. So if you'll notice here, the voltages cancel out, and we get this very nice expression for the equivalent capacitance, which is just the sum of these capacitances. And let me explain why that makes sense. So you had kind of these like 3 separate capacitors, but if you'll notice, they're not really separate. In fact, they're connected by this wire right here. And these 2 are connected by this wire right here. So it's almost as if, oh no, what happened? Okay, it's almost as if we could just extend these plates and nothing would change, except our capacitances would just be the sum of all the capacitances, and the charges would be the sum of all the charges. So yeah, that's parallel. And if you'll notice, this is just the relationship for resistors in series. And basically the reason we got that was because V is equal to Q over C, where C is inversely proportional to V as opposed to resistance, which is directly proportional. Okay, let's now do series. Okay, so before we do series, there's one thing I first have to convince you of, and that is that the charge that builds up in series on this plate is the same as the charge that builds up on the next one. And so on if I had more capacitors. And so again, how I'll demonstrate this, and then I'll give sort of a separate explanation that's, I think, probably taught in class as well. So the way first we can talk about it is with just this like proton view, where you have this one proton that's going to be repelling some proton over here, and it's going to build up on this plate right here. That proton is in turn going to repel another proton from here. And remember, there's an equivalent electron as well. But now there's going to be one less proton here that's going to be repelled by this guy. And that proton's going to build up on this other plate. And this guy is going to repel a proton from here. And that guy is going to move kind of all the way around our circuit until it gets back here, and then it'll be repelled and it'll build up on this plate. And that'll keep happening for every electron that's that builds up here. There's basically a proton being pushed away to the other plate, and every electron that's building up here is the same as the number of these. So that's kind of conceptually how it works. Another good way to think about it, which is actually a pretty important fact that you guys will use, is that we can separate this circuit in like these components, where I can kind of get rid of this part and say, okay, this part existed separately at some point. I can even kind of just keep this wire here, capacitor plate here, but I'm just going to keep this like one node. And what I can say is that when this existed separately, there was no net charge on it. So it was just like some random piece of metal. There's no need for there to be like a net charge unless you put one there. And we can easily just ground this. So once we do that, let's take this guy and put it back into our circuit. Oh, I can make it bigger. Nice. Yeah. So what we did now is we didn't change the fact that there's no net charge in this little component. And if you'll notice, there's no way for there to enter positive charge or leave positive charge. I know I've been talking about these like protons moving, but they're never crossing this air barrier, right? You cannot cross this area because air is basically not conductive, it's an insulator. And so the net charge on this guy cannot change. Yeah, so that's kind of the argument for why there's equivalent charge in series here. And let's write it out. So in series, we know what adds up is the voltages, because we know that the voltage you gain across the battery, some V, you're going to lose a portion of it across this capacitor, a portion of it across this capacitor until you get back to zero, right? That's Kirchhoff's loop rule. So we know that V1, V total, is equivalent to V1 plus V2. And we have our expression back here, which is Q equals CV. So then we can say that V total is equal to Q over C1 plus Q over C2. And this can be a Q2 and a Q1, except what we discovered was that this Q is actually the same. So then you can just factor this Q out and say, okay, this voltage is equal to this Q times 1 over C1 plus 1 over C2. And remember, this is some Q equivalent over some C equivalent. So conveniently, we can kind of just say that this Q equivalent can be like this other Q equivalent, and this C equivalent is going to be 1 over, remember, because we're dividing, 1 over this entire quantity. And I think, an easier way to see that is just like 1 over C equivalent is equal to 1 over C1 plus 1 over C2. That's the relationship we have in parallel.